Okay, so remember in simple harmonic motion, the restoring force on the object is directly proportional to the object's displacement from equilibrium, and it has the opposite sign. So in Newton's second law, we can replace the F, the force, with negative kx, where k is just a proportionality constant that depends on the system. If we have an oscillating system that involves an object on a spring, then the k will be the spring constant. And so we can solve for the acceleration of the object is going to be negative k over m times x. And so in simple harmonic motion, we have this differential equation because the acceleration, which is the second derivative of the displacement of the object, is proportional to the displacement x, and that proportionality constant is negative k over m. And so we can now introduce a new quantity called the angular frequency. And this is just 2 pi multiplied by the regular frequency. And so you can see here, we can replace the k over m with the angular frequency omega squared. And so then omega is equal to 2 pi times the frequency, or the square root of k over m, where k is the force constant and m is the mass of the object. And you can see, if we solve for the regular frequency, we get 1 over 2 pi times omega, which agrees with the equation that we found before. The frequency is 1 over 2 pi times the square root of k over m. And then we can also get the period equation, which is just the reciprocal of the frequency equation. So we have the same equations, but we now are using a new quantity, the angular frequency. So for the displacement of the object, remember we had these two equations, the cosine version and the sine version, depending on where the object started at time equals 0. And so we can rewrite these equations as well using the omega, the angular frequency. So notice how 2 pi divided by the period, if we just move this to the other side, it's the same thing as the square root of k over m. And we know that is just the angular frequency. So we can rewrite the displacement equation for simple harmonic motion as the amplitude times the cosine of omega times t, and then we have this thing called the phase angle. And this is to account for the cases where the object does not start at the maximum displacement or the equilibrium. Because remember here we had to have two equations depending on where the object started. So here, if we just use the phase angle, we can only have one equation, and we just change the value of the phase angle to match wherever the object starts. When the phase angle is 0, that means the object starts at the maximum displacement, because at t equals 0, the cosine will equal 1, which is so this will just equal the amplitude. So we just make the phase angle whatever we want, depending on where the object starts. Okay, so now we're going to look at a pendulum in more detail. So remember, in a pendulum, the restoring force is provided by gravity, and only the component of gravity which is tangential to the object's path. So we have the restoring force is equal to negative mg times the sine of this angle. And so this is not, you can see this is not exactly simple harmonic motion, because the restoring force is not directly proportional to the displacement. It's proportional to the sine of the angle. However, if the angle here is small enough, then we can approximate the sine of theta as just theta. So we can approximate this as simple harmonic motion when this angle is small. So we have the force is just negative mg times theta, and using the definition of a radian, the angle is just the arc length divided by the radius. We can replace theta with x over L, where x is just this arc length displacement of the object, and L is the length of the pendulum. So now we have the restoring force is directly proportional to the displacement from equilibrium. So this tells us that the force constant for a simple pendulum, the k, is going to be equal to mg over L. Because remember, we have the restoring force is equal to negative kx, where k is whatever the force constant is. And so, using this value of k, we can find the angular frequency for a simple pendulum, which is going to be the square root of g, the gravitational acceleration, divided by L, the length of the pendulum, which agrees with the equations we found earlier for a pendulum. So, a physical pendulum, we no longer have a point mass on a massless string, but we just have this big rigid body. So the equation is almost the same, except instead of a restoring force, we're going to have a restoring torque. So the tangential component of the gravity now provides a torque around this pivot point. So the force is still negative mg times the sine of theta, and then to get the torque, we just multiply the force by the lever arm, which is going to be this distance from the pivot point to the center of gravity, which we will call d. So the restoring torque is negative mg times d sine of theta. And then again, we can approximate sine of theta as theta if the angle is small enough. So we have the torque is equal to negative mg d theta. And using Newton's second law for rotational motion, this is also equal to the moment of inertia times the angular acceleration. And so then we can solve for the angular acceleration, and then we have the differential equation, which is characteristic of simple harmonic motion. See, we have the second derivative of the displacement is proportional to the displacement. And so this tells us, remember that in this equation for simple harmonic motion, we can see that this part, mgd over I, is equal to omega squared. So then for a physical pendulum, the angular frequency is the square root of m, the mass, times the gravitational acceleration, times the distance from the pivot point to the center of gravity, divided by the moment of inertia.